Welcome back to the deep dive. We are cutting straight through the noise of technical literature today, really diving deep into what feels like the next monumental shift in AI. We're talking about the race to build truly universal time series foundation models.
Exactly.
And if you're an AI researcher, maybe a quant analyst, or anyone managing large-scale infrastructure, whether it's industrial, financial,
Right.
the forecasting challenge, it's tough.
Oh, it's notoriously difficult. Time series data is,
Right.
well, it's just a beast, isn't it?
Right. You've got non-stationarity, these crazy outliers, really complex nonlinear patterns happening over time, and
Yeah.
often you need to predict way out into a future that's inherently uncertain.
Yeah, and building one single model that could handle, say, stock markets,
Yeah.
then switch to IoT sensor data, and then maybe tackle quarterly economic reports. I mean, that seemed like pure fantasy just a few years back.
It really did.
It was certainly an uphill battle. A lot of that was down to how forecasting was traditionally done, very localized, right? But then came the first generation of time series foundation models, TSFMs. We're talking about the pioneers here,
Yeah.
like TimeGPT, and maybe the early ideas behind models like MOIRAI and Chronos. And they proved one absolutely massive thing. Zero-shot forecasting is actually real. You could pre-train one big model on tons of diverse data and then just apply it straight away to a new time series, no costly retraining needed.
Which sounds amazing, right? But that brings us to the core mission for this deep dive, doesn't it?
It does. We're exploring that tension point, the friction that really kicked off this second wave of innovation.
Because while those first models, they looked great on paper, on the standard academic benchmarks.
Right. They aced the tests.
But the sources we're looking at show that when you put them up against complex, high-stakes, real-world customer data, well, those specialized, manually tuned baselines often still won.
Yeah, your highly engineered XGBoost models, maybe your custom MSTL decompositions, you often still had that critical edge in practice. There was this performance gap. The generalization wasn't always reliable enough.
And that's the killer problem, isn't it? If your fancy foundation model needs fine-tuning anyway to close that gap.
You've lost the magic.
Exactly. You're back to complexity. You're adding latency. It just completely defeats the whole point, the elegance of that zero-shot idea.
Precisely. So the research we're unpacking today, it shows how this second generation, and you hear names like MOIRAI-2, maybe TimesFM-2.5, Toto-2 being discussed conceptually, how they've tackled this head-on.
How? What did they change?
Well, it's a combination of things. Architectural breakthroughs, definitely. Much, much cleaner data curation, richer inputs being fed into the models, and just scaling the data regime by like an order of magnitude, sometimes more.
Okay, so we've got some heavy hitters to analyze today.
We do.
We'll kick off with TimeGPT, sort of the OG transformer in this space. Then we'll look at TimesFM from Google. They really champion that decoder-only approach and using synthetic data.
Very interesting angle there.
Then MOIRAI from Salesforce, which went deep on architectural fixes for dealing with super messy, heterogeneous data.
Yeah, the any-variate problem.
And finally, Toto from Datadog. This is the one that just hit that mind-boggling scale, 1 trillion data points focusing on those tricky observability metrics.
Right, so we're going to be dissecting their technical choices, looking at the trade-offs, and really understanding this new, highly specialized kind of arms race that's happening in time series AI.
Okay, let's start by maybe grounding ourselves a bit. Why was the forecasting community historically kind of resistant to deep learning? And why are foundation models now finally breaking through that resistance?
Well, historically, I think the resistance came down to a couple of things. Efficacy and explainability.
Okay.
Your traditional statistical methods, think ARIMA, ETS.
Yeah.
They were interpretable. You could understand the components. And crucially, they worked really, really well on smaller, cleaner data sets.
Right, the stuff you might see in a textbook.
Exactly. And when early deep learning models came along, they often struggled. They couldn't always capture complex seasonality as well as a simple MSTL model, for instance. Plus, they came with this huge computational overhead.
So they were complex and didn't always beat the simpler stuff.
Pretty much. But foundation models, they overcome this resistance because they promise to just eliminate that whole complex manual forecasting pipeline.
Explain that pipeline a bit. What does it usually involve?
Okay, so a traditional workflow, you need an expert. They've got to look at the series, maybe decompose it, manually pick features like holidays or economic indicators. Then they have to choose the right statistical model, maybe ARIMA, maybe something else, and then tune its parameters specifically for that one series.
Wow, okay. That sounds incredibly labor-intensive, especially at scale.
It is. TSFMs, on the other hand, They simplify all of that down to potentially just a single inference step. You feed in the historical data, and the model, which has already learned from billions, maybe trillions of diverse patterns, just spits out the forecast.
That simplicity is definitely the big selling point. But let's circle back to that zero-shot cap we mentioned. TimeGPT showed it was possible that scaling laws could apply to time series too. But where exactly did it fall short? Where did those customized models still win in the real world?
Yeah, that's the crucial point. I think it boiled down to maybe three main things. Really specialized outlier handling, very domain-specific seasonality, and dealing with extreme non-stationarity.
Okay.
TimeGPT-1, being the pioneer, it used an encoder-decoder transformer structure. And it was trained on what was, at the time, the largest collection of publicly available data, which was still huge, over 100 billion data points.
That sounds massive.
It was. And that diversity definitely helped it learn general patterns, spikes, cycles, trends.
Because always a but.
Always. Real-world systems, especially proprietary ones, they just have unique noise characteristics, things the public data might not fully capture.
Like what? Give me an example.
Okay, so maybe a finely tuned model, trained only on financial data, knows exactly how to handle a weird intraday trading glitch, an outlier specific to that market. Or maybe a manufacturing process has a seasonal pattern tied to a very specific local holiday that just wasn't in the big general training data set.
Okay. So the first-gen TSFMs were great generalists, but sometimes they smoothed over those really critical, fine-grained local details.
You got it. The architecture was trying to be global, universal, but the task often demanded really specific local precision. They demonstrated universality, but sometimes at the cost of accuracy against a hyper-focused, specialized model.
So the architecture was global, but the task required local precision. The first generation was demonstrating universality, but occasionally sacrificing accuracy against a hyper-focused opponent.
Exactly right. And the obvious first thought was, okay, let's try fine-tuning. Take the pre-trained model, run a few more training steps just on the target data.
Makes sense.
It does until you scale it. Imagine you have, say, 10,000 different customers, and each one has 50 different time series they care about.
Okay, so 500,000 time series.
Right. Now imagine managing 500,000 separate fine-tuned models. The latency, the complexity.
Yeah.
It completely wipes out the benefit of having that single foundation model in the first place.
Yeah, you're back to square one, almost.
Pretty much. So the conclusion was clear.
Oh.
We need better pre-training, cleaner data, richer data, maybe different architectures, so that the zero-shot inference itself is just so robust that you don't even need to think about fine-tuning.
And that realization is what catalyzed this explosion in architectural innovation we're seeing now with TimesFM, MOIRAI, Toto, and likely others.
That's the story.
Okay, let's jump into that second wave then, starting with TimesFM from Google Research. Their philosophy seems really focused on efficiency and getting that zero-shot capability rock solid. And they were explicitly aiming to do better than just adapting generic large language models, right?
That's spot on. Adapting LLMs like, say, Llama or GPT-3 directly for time series forecasting. It often doesn't work that well in zero-shot mode.
Why not?
Well, fundamentally, those models are trained on language, on semantic tokens. They don't inherently understand the mathematical structure of time series data, the temporal dependencies, the seasonality in the same native way. TimesFM was designed from the ground up to speak the language of time series.
Gotcha. So architecturally, TimesFM made a pretty big shift from TimeGPT-1's encoder-decoder setup. They went for a decoder-only attention model. That sounds a lot like the GPT architecture in NLP, doesn't it?
It's very analogous, yeah. And that choice brings some key technical benefits.
Like what?
Well, for one, the decoder-only model is structurally simpler. The training objective is more straightforward. Just predict the next token, or in this case, the next patch of time series data.
Okay.
And critically, it naturally supports auto-regressive generation. That's essential if you want to forecast arbitrarily long horizons into the future. Because you don't have a separate encoder stage, the computation is more unified. And that often makes it easier to optimize for massive parallelization during that expensive pre-training phase.
Okay, simpler, good for long forecasts. But you mentioned efficiency as a key driver. What's the big technical trick they use to make the transformer efficient for these really long time series sequences?
That would be patching. Patching is absolutely essential here.
Explain patching. How does that work?
Okay, so imagine you treat every single time step in your series as an individual token for the transformer. If you want, say, 10,000 time steps of history as context.
Which you might for long-term patterns.
Exactly. But the transformer's attention mechanism has a computational complexity that scales quadratically with the sequence length. It's ON2, where n is the length.
So, 10,000 squared, that's 100 million operations just for one attention head, roughly. That sounds bad.
It's computationally explosive. It quickly becomes completely impractical. So TimesFM introduces patches. These are just segments of the time series. Let's say each patch is 32 time steps long. These patches now become the new input tokens for the transformer. So if your total context n is 10,000 steps and your patch length p is 32, your effective sequence length for the transformer is now n divided by p, which is about 312 tokens.
Ah, so you go from 10,000 squared down to 312 squared.
Precisely. It's a massive, massive reduction in that quadratic cost. It makes using deep context practical and speeds up inference significantly.
That makes a ton of sense from an engineering perspective. But wait, traditional autoregression, where you predict the very next token, then the next, one by one, that's usually quite slow for generating long forecasts, right? And errors can build up. How does TimesFM, being decoder only, get around that?
Yeah, that's a great question. And this is where their specific patching design is quite clever. They use longer output patches.
Longer output patches, what does that mean?
So instead of having the output patch length match the input patch length, like predicting the next 32 steps based on the previous 32-step patch, they deliberately make the patch the model predicts longer. Maybe the input patch is 32 steps, but the output patch it predicts is, say, 128 steps long.
I see. So in one go, it predicts a bigger chunk of the future.
Exactly. And this dramatically cuts down the number of autoregressive steps you need to take. If you want to forecast, say, 512 steps ahead.
Okay.
A traditional step-by-step model, or even one using 32-step patches, might need 16 prediction steps. But TimesFM predicting 128 steps at a time only needs 4 steps.
Fewer steps means less chance for errors to compound and faster generation.
You got it. Less error propagation, more stability, much faster long horizon inference. It's a really smart way to blend the efficiency benefits of autoregression with the accuracy you get from more direct prediction methods.
Okay, let's talk scale and data for TimesFM. They trained on, again, a huge amount of data order of 100 billion time points, mostly from Google Trends and Wikipedia page views. But what struck me was their heavy use of synthetic data alongside that. Why did they need millions of synthesized series when they already had 100 billion real data points?
That's a really revealing insight, isn't it? It points to a fundamental limitation, even in massive real-world datasets. They often lack diversity across all the possible granularities or frequencies you might encounter.
What do you mean by granularities?
Like how often the data points are recorded. Real-world data tends to be heavily clustered around common frequencies, daily data, hourly data, maybe monthly. And these frequencies often have typical seasonal patterns associated with them.
Okay.
If your model only sees those common patterns during training, it might struggle to generalize well to less common frequencies it hasn't seen much of. Think about quarterly economic data maybe, or sensor data recorded every 15 minutes. These can have totally different noise profiles, different kinds of temporal dependencies.
So the real data, even 100 billion points, had blind spots.
Sort of, yeah. So they generated 3 million synthetic time series, each one 48 steps long. And these weren't just random noise. They were carefully constructed using combinations of classic statistical patterns, ARIMA processes, different kinds of seasonal cycles, various trends, different types of noise added in.
They basically engineered the diversity they needed.
Exactly. And their ablation studies where they tested the model with and without the synthetic data proved it was necessary. When they removed the synthetic data, performance dropped noticeably on datasets with those less common granularities like the higher frequency ETTM datasets.
Wow. So it showed that sheer volume isn't enough. You absolutely need that engineered diversity in the training mix to get true zero-shot generalization across all sorts of time series.
That seems to be the key lesson. And the results really back it up. TimesFM hit top performance on the standard Monash datasets, and importantly, it performed comparably to supervised state-of-the-art models like Patch TST on some key benchmarks like the Informer datasets, all in zero-shot mode.
So they effectively showed that this decoders-only approach, combined with patching and that engineered data diversity, could indeed close that zero-shot gap we talked about earlier.
Yeah, a very strong demonstration. Okay, so if TimesFM was really pushing on architectural efficiency and leveraging synthetic data, MOIRAI took a slightly different path.
This is the one from Salesforce AI Research, right? Masked encoder-based universal time series forecasting transformer. Quite a mouthful.
It is. MOIRAI. Their big focus was squarely on tackling the inherent heterogeneity you find in massive, real-world time series collections. They use an encoder-only architecture this time, specifically a masked encoder, recognizing that time series data in the wild is just messy. It's non-uniform.
Let's break down that heterogeneity. What were the key types of messiness that MOIRAI specifically set out to solve, maybe things that earlier models hadn't fully addressed?
Right. They really highlighted three crucial forms of heterogeneity. First was cross-frequency learning.
Okay, like mixing hourly and quarterly data again.
Exactly. How do you get one model to effectively learn useful patterns from super high-frequency web traffic and very low-frequency GDP data simultaneously without one watching out the other?
Challenge number one. What's next?
Second was univariate scaling. This is a big one. How does the model handle multivariate data with multiple related series, when one user might give you 3 metrics to forecast together and the next user might give you 30? And it has to do this on the fly in a zero-shot setting.
Right, because different customers monitor different things. You can't pre-train a separate model for every possible number of input variables.
Precisely. And the third challenge was distributional heterogeneity. Basically recognizing that different types of time series data follow fundamentally different statistical distributions.
Like sales counts versus sensor readings.
Yeah. Sales counts might follow something like a negative binomial distribution, positive integers, often skewed. Sensor readings might be closer to Gaussian, or maybe students T if they have outliers. Financial returns might be log normal. How does one model handle all these different underlying data generation processes gracefully?
Okay, 3 big challenges: frequency, number of variables, and the underlying statistics. Let's tackle the univariate problem first. How did MOIRAI's architecture handle an arbitrary number of input series or variates? Most transformer inputs need a fixed size, don't they?
They typically do. MOIRAI's solution here is really clever. It involves a combination of flattening the input and using some subtle attention biasing.
Flattening.
Yeah, instead of trying to maintain separate channels or dimensions for each variate, they basically flatten the multivariate series into one single long sequence of tokens. So if you have, say, 5 variates and each has 100 time steps.
You get 500 time steps total.
No, you get one sequence of 500 tokens. The first 100 tokens are variate 1, the next 100 are variate 2, and so on.
Ah, okay. But then how does the model know which token belongs to which original variate and which time step? Doesn't it lose that crucial information?
That's where the positional information comes in. They use rotary position embeddings, ROPE, which is pretty standard now, to encode the time index. But for the variate index, they do something really neat. They use binary attention biases.
Binary attention biases, what are those?
It's surprisingly simple. They have just 2 extra learnable scalar parameters, let's call them beta same, and beta different.
Okay.
When the attention mechanism is calculating the score between a query token and the key token, if both tokens originally came from the same variate, like comparing this week's temperature to last week's temperature.
It adds beta same.
Right. And if the query and key tokens came from different variates, like comparing this week's temperature to this week's rainfall.
It adds.
Exactly. So these 2 learned numbers subtly nudge the attention mechanism. They teach it to inherently understand whether it's looking at a relationship within a single variate over time or a relationship between different variates at potentially different times.
Wow. That's elegantly simple. Just 2 numbers control how it sees cross-variate relationships.
Pretty much. And this minimalist approach works. It effectively encodes the variate structure, and importantly, it satisfies a property called permutation equivariance, meaning the model's output doesn't change if you just reorder the input variates.
Which is crucial because the order shouldn't matter.
Right. And the beauty is, this design means the model can accept 20 variates 1 minute and just 2 variates the next, without needing any change to its core structure or requiring any fine-tuning. It's fundamentally scalable in that spatial or variate dimension.
Okay, that's a really neat solution for the univariate problem. How do they tackle the cross-frequency challenge? You mentioned the multi-patch size projection.
Yes. This directly addresses that temporal heterogeneity, the mixing of hourly and monthly data, for instance.
Because a patch size that works well for one might be terrible for the other, right?
Absolutely. Think about it. A patch size of, say, 100 steps. For hourly data, that captures maybe 4 days of context. Pretty reasonable. But for monthly data, a 100-step patch covers over 8 years. You're averaging out way too much detail, losing the fine-grained patterns.
Okay, so how does multi-patch size projection fix that?
MOIRAI's approach is to have multiple sets of input and output projection layers within the model. Each set is associated with a different predefined patch size, chosen to be suitable for a particular frequency band. Maybe one set for high-frequency data, small patches, one for medium, one for low, larger patches.
So when data comes in, the model somehow knows which set of projection layers and which patch size to use.
Essentially, yes.
Yeah.
Based on the data's inferred frequency, it routes the input through the specialized projection layers designed for that frequency's typical patch size. This prevents that knowledge dilution where trying to handle all frequencies with one patch size forces a bad compromise. Instead, the model learns frequency-specific representations more effectively.
Clever. It specializes parts of the network for different timescales. Okay, that covers frequency and variates. What about the third, heterogeneity? The different statistical distributions. How did MOIRAI handle probabilistic forecasting for all those different data types?
Right, so just using a single robust distribution, like maybe the student's T distribution, which is good for handling outliers, that often isn't enough.
Why not? Student Steve sounds pretty flexible.
It is, but real-world processes generate data with fundamentally different shapes. Forecasting sales counts, like we said, needs a distribution that's focused on positive integers, maybe skewed. Latency data might be continuous, but also heavily skewed. Using just one distribution type, even a robust one like student's T, forces the model to try and approximate a shape that it might not naturally match.
So you lose precision in the probabilistic forecast, in the uncertainty estimate.
Exactly. So MOIRAI introduced a mixture of parametric distributions. They combined 4 distinct distribution types within their prediction head.
Okay, what were they?
First, the student's T distribution. That's your robust workhorse for continuous data, good at handling heavy tails like outliers.
Got it.
Second, the negative binomial distribution. This one is absolutely essential if you want to accurately model positive count data, things like the number of website clicks or units sold. It naturally handles integer counts and over-dispersion.
Okay, makes sense for counts. Third.
The log normal distribution. This is ideal for data that's strictly positive and often highly skewed to the right, like maybe certain financial returns or some types of latency measurements.
Right, things that can't be negative and have long tails.
Mhm.
And the fourth.
Finally, they included a low variance normal distribution. This one is kind of interesting. It's used almost as a signal. If the model is highly confident about its prediction and expects very little noise, it can put weight on this narrow Gaussian to indicate that high certainty.
Wow. So the model doesn't just output a single forecast. It actually outputs the parameters for all 4 of these distributions, and then it learns how to blend them, how to weight them for each specific forecast.
That's exactly right. It learns to pick the right distributional shape or combination of shapes for the specific data point it's forecasting.
That sounds incredibly sophisticated, but it allows for really flexible and hopefully accurate modeling of the uncertainty, right? Which is critical if you care about things like prediction intervals measured by metrics like CRPS or MSIS.
Precisely. This allows for genuinely robust probabilistic forecasting across wildly different data types. But, as you can imagine, teaching a model to do this requires a lot of diverse data.
Which brings us to their training data.
Yeah, MOIRAI was pre-trained on the large-scale Open Time Series archive, or LATSA. This dataset contained over 27 billion observations across 9 really big domains. And they trained models ranging from a small 14 million parameter version up to a large one with 311 million parameters.
And did they test if these complex architectural pieces, the any varied attention, the multi-patch size, were actually necessary?
They did. Their ablation studies were crucial. They showed that if you removed either the any varied attention mechanism or the multi-patch size component, the model's performance dropped significantly. It really confirmed that these specialized architectural solutions were essential for handling that massive scale and heterogeneity effectively.
Okay, now we get to Toto from
Yeah.
Datadog. And if MOIRAI was about tackling curated diversity across, 27 billion points.
Yeah, 27 billion observations in LATSA.
Toto just took the scale challenge and absolutely smashed it. We are talking about a model trained on 1 trillion time series data points.
1 trillion. It's almost hard to comprehend that scale, isn't it?
It really is. I mean, a low KSA, which sounded huge, is measured in tens of billions. Toto is operating in the trillions. And crucially, this isn't just more public data. A huge chunk of it, maybe 75%, is proprietary anonymized observability metric data from Datadog's own systems.
Right, things like CPU utilization, network latency, application error rates. And this represents a really fundamental shift, moving beyond diverse but perhaps somewhat generic public benchmarks into the specific messy reality of large-scale industrial IT infrastructure.
And that kind of data comes with its own unique set of challenges, doesn't it?
Oh, absolutely. That scale is the headline, for sure. But the nature of that observability data is really the key technical driver behind Toto's design. This stuff is notoriously difficult to model.
Why? What makes it so tough?
Well, you've got a few key characteristics. One is extreme right skew. Think about error counts or latency metrics. Most of the time they might be low, but then they can spike dramatically, unpredictably. The data distributions have these incredibly heavy tails.
Okay, massive spikes. What else?
Sparsity, or maybe more accurately, zero inflation. For many metrics, like error counts again, the value is actually zero most of the time. No errors happening or maybe very low system usage. Modeling those zeros correctly is tricky.
Right, it's not just continuous data. And the third,
Non-stationarity. Cloud infrastructure, microservices. They change constantly. New services get deployed, old ones get updated, traffic patterns shift. Past behavior isn't always a reliable guide to the future, so the model needs to adapt quickly.
so heavy tails, lots of zeros, and constantly changing patterns. That sounds like a nightmare for forecasting.
It is. So Toto, which interestingly is also a decoder-only model like TimesFM, needed really specialized solutions. It had to handle the sheer high-dimensionality monitoring potentially thousands of interrelated services, and it had to model that extreme noise and skewness robustly.
Let's talk about that high dimensionality first. How does it handle potentially thousands of metrics simultaneously, full attention across all metrics, and long time horizons? Seems like it would hit that ON2 problem again, but even worse.
Exactly. It would be completely computationally infeasible. So Toto uses a mechanism they call proportional factorized space-time attention.
Factorized. That sounds like it's breaking the problem down.
It is. It's a solution born out of necessity, really. It separates the attention calculation into two distinct types of interaction, which are handled by alternating blocks within the model architecture.
What are the two types?
You have temporal blocks, or time-wise blocks. These focus on capturing relationships within a single metric across different points in time, looking for trends, seasonality, cycles, just within, say, the CPU load of one service.
Okay, looking along the time axis for one metric and the other type.
Then you have channel blocks, or space-wise blocks. These focus on capturing interactions across different metrics or series, but typically at a single point in time, or maybe over a short window. So this is where the model learns how a spike in service A might relate to a change in service B.
Okay, so it alternates between looking a long time for one metric and looking across metrics at one time. But the name includes proportional. What does that part mean?
That refers to the fact that they don't necessarily have an equal number of time-wise and space-wise blocks. They can configure the ratio. The paper mentions often using a ratio like 2 time-wise blocks for every 1 space-wise block.
Where? So they're dedicating more compute, roughly 2/3 to the temporal dimension and less to the cross-metric dimension. Doesn't that risk missing crucial correlations between services, especially maybe during a fast-breaking incident or outage?
That's an excellent critical question. And yes, you are potentially trading off some immediacy in detecting those cross-service correlations. But the architectural choice is really justified by the general dynamics typically observed in this kind of data.
How so?
For the vast majority of forecasting tasks in observability, the temporal dynamics, the trend, the seasonality, the recent history within a single metric tend to be the most powerful predictors of its near-future behavior. A single service's CPU load over the last hour is usually a much stronger indicator of its load in the next 10 minutes than a sudden momentary spike in some other possibly unrelated service.
Okay, so they're betting that understanding the self-history is usually more important than the cross-history.
Kind of. It's an efficiency trade-off. That 2.1 ratio dedicates more computational power to refining the understanding of those crucial temporal patterns, while the single space-wise block still ensures that essential cross-service dependencies can be captured, just maybe with slightly less focus or frequency. This factorized approach is what makes the computation feasible at that trillion-point scale, without completely sacrificing the ability to model cross-metric effects.
Right. It's a pragmatic engineering choice driven by the data characteristics and scale. Okay, that covers the attention. Now, what about modeling those extreme distributions? The heavy tails, the skewness. You said Toto had to go even further than MOIRAI's mixture approach.
Yeah, they introduced something called the student T mixture model, like SMM head.
Okay, student T mixture model. How is that different from MOIRAI's mixture?
The key difference is what's in the mixture. Remember, MOIRAI used a mixture of different types of distributions, student T, negative binomial, log normal, to model different fundamental data types, continuous, counts, skewed.
Right.
Toto's SMM, on the other hand, uses a mixture of the same robust distribution type, the student T distribution,
Why stick to just student T?
because the student T distribution itself is inherently more robust to outliers and heavy tails than, say, a Gaussian normal distribution. Its tails decay much more slowly, mathematically speaking, so it's already well suited for data with extreme values.
Okay, so it starts with a good base for heavy tails. Why use a mixture of them then?
Using a mixture of multiple student T components achieves two really important goals for observability data. First, it makes the overall model even more robust to those wild spikes and extreme values. Second, the different components in the mixture allow the model to capture multimodality.
Multimodality, meaning the data might have multiple peaks or common states.
Exactly. Think of a system that might predictably operate in a low-load state most of the time, but occasionally switch to a distinct high-load state. Each state might have its own typical value and variability, its own distribution shape. A mixture model can learn to represent both of those states simultaneously.
Ah, I see. So the SMM head is specifically tuned to handle both the extreme outliers and potential multiple operating modes common in infrastructure metrics.
Precisely. And having that accurate distributional understanding is absolutely critical if you want to provide genuinely reliable prediction intervals or set meaningful anomaly detection thresholds for infrastructure monitoring. A simple point forecast isn't enough. You need to know the plausible range.
And did this specialized architecture and the massive domain-specific data actually pay off in performance?
It seems so, particularly where it counts most on their own challenging data. They developed a dedicated Datadog observability benchmark designed specifically to reflect the tough characteristics of their trillion-point dataset.
And how did Toto do?
On that benchmark, Toto reportedly achieved better scores on key metrics like SEM-APE, symmetric mean absolute percentage error, and particularly SMD-APE, symmetric median absolute percentage error, which is more robust to outliers, compared to other strong zero-shot foundation models like Chronos and even MOIRAI.
So that really highlights the value of training on data that closely matches the target domain, doesn't it? Even if that data is massive and incredibly challenging.
Absolutely. It strongly suggests that the kind of generalizability learned from broad public benchmarks, while valuable, might not be enough to fully replicate the specialized knowledge you gain from training on a trillion points of real, messy, operational infrastructure telemetry. Domain specificity at scale seems to provide a significant edge for these tough, real-world problems. Okay, so we dissected these key second-generation models, TimesFM, MOIRAI, Toto building on the foundation laid by pioneers like TimeGPT. If we step back now, we can definitely see some clear patterns emerging, some technological convergence happening in state-of-the-art TSFMs.
What are the big common threads you're seeing across these successful models?
Well, first and foremost, the transformer architecture is absolutely dominant. There's just no question. Whether it's the original encoder-decoder like TimeGPT, or the encoder-only masked approach of MOIRAI, or the decoder-only style of TimesFM and Toto. The core engine is the attention mechanism. It's proven uniquely capable of capturing those complex nonlinear dependencies over really long time horizons.
So attention is king. What's the second commonality?
Patching is mandatory. We saw it in TimesFM, MOIRAI, and Toto also uses a form of patching or segmentation. The computational economics just demand it. You cannot feasibly run vanilla attention over tens of thousands of raw time steps. Every successful large-scale model relies on breaking the time series into these segments or patches to manage that quadratic complexity. It's what makes longer context windows and faster inference actually possible.
Right, patching unlocks the scale. And the third convergence seems to be around handling uncertainty, moving beyond simple point forecasts.
Definitely. This is maybe the most interesting mathematical convergence. We're seeing a universal embrace of probabilistic sophistication. The simple Gaussian distribution, assuming nice, well-behaved noise.
Yeah.
That's just not cutting it for high-stakes, real-world forecasting anymore.
So what are they using instead?
Advanced mixture models are becoming standard practice. It's no longer enough to just give a single best guess. You have to provide reliable uncertainty quantification prediction intervals. MOIRAI uses that clever mixture of different distributions tailored to handle data type heterogeneity counts, continuous, skewed data. Toto uses the student T mixture model, which is optimized for modeling the inherently heavy-tailed nature of their specific observability data. But both approaches show this deep commitment to moving beyond simplistic assumptions and accurately modeling the complex, non-Gaussian noise and uncertainty that you actually find in the real world.
Okay, so transformer core, patching for efficiency and sophisticated probabilistic outputs. Beyond the architecture, though, the other unavoidable theme is just the staggering amount of data involved.
Oh yeah. The prerequisite for even playing in this second-generation TSFM game seems to be sheer data scale. There's a clear progression.
Walk us through that scaling again.
TimeGPT sort of established the baseline, using over 100 billion publicly available points. TimesFM replicated that order of magnitude around 100 billion, but crucially added synthetic data to boost diversity. MOIRAI used the highly curated Lotsessa dataset with 27 billion ultra-diverse observations. And then Toto just blew the doors off, hitting the 1 trillion point mark, albeit with very domain-specific data.
So the scale is just relentlessly increasing.
Dramatically. But, and this is the crucial lesson, I think, highlighted by both TimesFM's synthetic data and MOIRAI's architectural choices, volume is only half the equation. Diversity is just as critical, maybe even more so in some ways.
Yeah.
Meaning you need those synthetic patterns like TimesFM used to fill the gaps in real data, to cover those underrepresented frequencies or event types. And you need specialized architectural components, like MOIRAI's multi-patch size projection or any varied attention, specifically designed to handle the intrinsic heterogeneity found in diverse datasets. Otherwise, just piling on more data might actually dilute the useful signal or fail to generalize properly. Scale needs to be paired with smart handling of diversity.
That makes sense. Scale plus targeted diversity plus smart architecture. Now, this level of scale, it inevitably brings us to the economics. Training these models must be incredibly expensive.
Immense.
The sources, especially the TimesFM paper, they talk about confirming scaling laws for a time series, basically, showing that performance keeps getting better the more compute and data you throw at it. Given that massive upfront training investment, where's the ROI? Is it purely about making the zero-shot inference cheaper or faster later on?
That is precisely the calculation, yes. The training cost is immense. You know, the TimesFM paper mentioned their 200 million parameter model trained for about 2 days on a pretty beefy TPU setup that's a lot of compute time and energy.
Okay.
But that cost is viewed as a one-time capital investment to acquire this highly generalized temporal intelligence baked into the model weights.
And the payoff comes at inference time.
Instantly. Every time you use the model for a forecast. Consider the alternative they were comparing against, adapting general LLMs. One paper they cited studying specialized LLM forecasters mentioned needing something like an AWS instance with 8 high-end NVIDIA V100 GPUs, the 32GB version, just to run inference in zero-shot mode.
Wow, 8 V100s just to make one prediction. That's incredibly expensive.
Exactly. These specialized TSFMs like TimesFM or MOIRAI or Toto, once that massive pre-training is done, they can deliver Euro-shot predictions that, as we've discussed, now often match or beat highly tuned traditional baselines, potentially much, much cheaper and faster per inference than trying to repurpose a giant general-purpose LLM for the task.
So the foundation model approach fundamentally shifts the economics. Instead of a high ongoing cost for customizing or running inference for every single time series, you have a massive upfront cost amortized over potentially billions of future low-cost generalized inference calls.
You've nailed it. It's kind of the ultimate democratization or maybe industrialization of high-quality forecasting. It shifts the really heavy computational burden away from the end user who just wants a quick, reliable forecast and places it onto the research lab or the platform provider doing the pre-training. These models aren't just technically impressive, they represent a potentially transformative economic model for anyone needing to forecast at massive scale. #outro.
This has been a fascinating journey. We've really witnessed a breathtaking evolution today, haven't we? That zero-shot gap, the sort of Achilles heel of the first-generation time series foundation models, it seems to have been effectively closed, or at least significantly narrowed, by the second wave we've discussed models like TimesFM, MOIRAI, and Toto.
Yeah, it feels like a real step change.
And they've done it not just by getting bigger, though the scale is certainly part of it, but by getting architecturally smarter. Using patching for efficiency, developing specialized attention mechanisms like factorized attention or any variant biasing for complexity, and building these really robust mixture models to handle real-world uncertainty.
Exactly. The combination of scale, architectural innovation, tailored to time series properties, and that sophisticated probabilistic modeling seems to be the winning formula right now.
So where do we go from here? What's the next frontier, based on the hints in these papers?
Well, the sources and just the logical progression, I think, point pretty clearly towards the next big challenge, maybe the third generation.
Gotcha.
If these specialized TSFMs can already capture such complex temporal dynamics, even at the trillion-point scale, the next logical step is to combine that deep temporal intelligence with broader contextual awareness.
Contextual awareness. You mean like bringing in other types of data?
Exactly. Think about the future of multimodal integration. What happens when you can fuse the TSFM's incredibly detailed understanding of, say, network latency patterns with the kind of textual context that a traditional large language model understands? Maybe reading news articles that mention a potential cyber attack targeting that network, or analyzing social media chatter about a new product launch that might impact website traffic.
Ah, so you're talking about merging the TSFM's numerical time-indexed world with the semantic, textual, maybe even visual world that LLMs handle.
Precisely. That fusion, that ability to reason jointly across time series data and unstructured text or metadata or maybe even video, that feels like it could unlock entirely new classes of forecasting and anomaly detection problems.
Wow. Can you give an example? What kind of systems become predictable then?
We'll think bigger picture. What entire infrastructure systems or complex economic systems or even climate systems might become fully transparent, fully predictable when you can unify the intricate temporal patterns from sensor data with the human context from news, reports, and other sources, all within a single, maybe third-generation foundation model.
That's a pretty profound thought, fusing time, data, and context at scale.
It is. That convergence seems like the ultimate objective down the road, and the really sophisticated, specialized TSFM research we've explored today, models like TimesFM, MOIRAI, Toto, they feel like the absolutely necessary technical bedrock, the prerequisite for even attempting that grander fusion in the future.
A fascinating place to leave it. Thank you for that deep dive.
My pleasure.